All right, we just talked about motivations for the exponential distribution. Now here's the definition. We say that x is distributed as exponential, or exp, lambda, if it has the PDF. Here f of little x, this is the PDF, the probability density function, should be equal to lambda times e to the negative lambda x for x positive. So these are waiting times, so they must be positive, and 0 for x less than or equal to 0. So this is a continuous random variable used to model wait times. It has these properties, so the mean of x is equal to 1 over lambda, and the variance, sigma squared x, is equal to 1 over lambda squared. One nice thing about this PDF is that we can actually compute a closed form of the CDF, the cumulative distribution function. So f of little x, recall this is the probability that the random variable x is less than or equal to a particular value of x, which is defined to be the integral from negative infinity to infinity of f of x dx. I'm sorry, not to infinity, just to x. And also we need to replace these x's with the dummy variable t, because they're going to be integrated out. So we plug that into our equation here. We get negative infinity all the way up to t, f of t, lambda e to the negative lambda t dt. I'm sorry, this is not t, this is x. So this is a problem. It's not what we want. If we look over here, the PDF is 0 for x less than 0, so that should be out of our integral. So we can take that out by only starting the integral at 0. So we start from 0 here. Okay, and we can solve this integral. It equals lambda times e to the negative lambda t divided by negative lambda, evaluated from 0 to x, which is equal to negative e to the negative lambda t, evaluated from 0 to x, which is equal to negative e to the negative lambda x minus negative e to the negative lambda times 0, which is equal to this term inside here. Anything to the power of 0 is just 0. I'm sorry, it's just 1. So 1. We have negative and a negative here. It becomes a positive 1 minus e to the negative lambda x. So a nice closed form for the cumulative distribution function.